Hello, in the last video we discussed what is Sieve, its time complexity and few basics of number theory. Let's discuss the next part with other question. Pause the video here and read the question and give it a try. So let a tree exist with a root value n. The property of this tree is each of its node branches out to nodes with a value equal to one of its divisors except one and the number itself. What maximum height the tree can have? The height of a tree is defined as the number of edges in its longest path from root to leaf node. For example, the root value is n. It can branch out to 2 and 4, and the 4 can again branch out with value 2. So the maximum height is 2 because the path looks like 8 4 2. So for given value 8, the answer is 2 because we can have 8 4 2, and the constraints are n can go up to 1 is 6. So according to the question, we want the highest number that is possible, highest height of tree. So it is possible if we can get maximum number, because for example if the number is 8, if we just try to, for example if the number is 8 and we have two choices x1 and x2 which are replaceable, it is surely better to keep the highest number as the first priority because it can have many other and we can have maximum height than all the possible cases. So we try to keep maximum value here if there are many choices. So the number is highest number possible into its pair. Its pair, for example, the number is 32 and we have two choices 2 and 16. We will prefer 16 obviously because this is the highest number possible, and its pair is x, which is 2. So x is the smallest prime factor because the smallest one is prime factor. So for 32 the smallest prime factor is 2, and the best number that is suitable to extend out now is the 32 by its smallest prime factor, which is 16. So the question boils down to find the smallest prime factor of number, and we can replace the number with num by the smallest prime factor we found. So how to find the smallest prime factor? Coming to again basic idea, we can traverse all the numbers from 2 till n, and if we find it is a prime according to Sieve, return that number because we found the smallest prime factor, and the time complexity of this will be of n because we are traversing all numbers from 2 to n, so it is of n. Now can we reduce it further? Because we want the maximum length, because we want to find smallest prime factor for every number. For example, if we are able to find the answer for 32, we have to find it for 16 as well in the next iteration, and similarly for the next 8, and similarly 4 and so on. So as the number increases, we want to do the highest number of smallest prime factors which can exceed the time limit. So it's better to optimize time complexity. So if we see the code of Sieve, we are starting from 2 till max, and if it is prime we are marking all the multiples of it as non-prime. So what if we are traversing through its multiples, and for example if the number is 2 and the numbers that are affected by these are 4 6 8 and so on. Similarly for 3, the numbers that are affected by these are starting from 9 because it will start from I square as we discussed in the previous video. So 9 12 and so on. And similarly for 5, the first number will be 25 and so on. So if we are traversing from I square, we are making it prime. Initially all small prime factors are 0, and if the smallest prime factor of j is 0, it means that we found a prime factor, because up to now there are no prime factors of this because it is also 0 now, because initially it is 0, and similarly after some iterations we found it as 0. So it means that we did not find any small prime factor than this, but now as we reached j, we got a prime factor I. So surely this is the smallest one. So we can replace smallest prime factor of j by I, so that it will not be replaced in the future iterations, and we got the smallest prime factor just in small modification of the Sieve. So in this way we can pre-compute SPF of all the values, and we can just use a loop and find from the starting number its smallest prime factor, and the next will be 32 divided by that number, and similarly smallest prime factor of this and divide by the next pair number and so on. So we can get this in O of 1 as we have pre-computed by using SPF. So some of its modifications can be the large prime factor and kth prime factor. So we have updated SPF of j is equal to I when it is 0, because we did not find any small prime factor till now, and now we found the number I, which is prime and the smallest till now. So what if we want to find the largest prime factor? So what if we update LPF of j I always, because as soon as we found I, for example, if there are many prime factors of a number, for example, the given number is 30 and the prime factors of it are 2, 3 and 5. So we are traversing from 2, it is a multiple. So initially the smallest prime factor is 0 and now it will become 2 and so on. Now coming to 3, the SPF is no longer 0 because it is 2. But in the all prime factors so far, the largest prime factor is now, because this is the latest one. So we can update LPF of LPF of 30 to 3. Similarly, we start with 5 and SPF is not modifiable because it is not 0. And we can update LPF because it is the highest prime factor so far. So without any condition, if we just update LPF of j is equal to I in the every loop, we can find the maximum prime factor. Similarly, if we want to find the kth prime factor of given numbers, we can just maintain a count and check if the number is less than or equal to k, we can update, and if the number is equal to k, it's our answer. So initially the smallest prime factor is the first prime factor. So similarly, in the way of kth prime factor, we can find the first prime factor as well, which is SPF. So let's check the code. It's exactly same as before. We are traversing from 2 till max, and if we found a prime number, we are traversing all its multiples. And if the SPF of 0, which means that we did not find any small prime factor till now, and now it will be the smallest prime factor, so it is I. And we want to find LPF, we can always update it so that the latest number will be the highest prime factor so far. So it will be and so on. We can return both SPF and LPF, and we can get in off one. But there is a small catch. For example, we are updating the sizes of SPF and LPF, and we are returning it, and now we are printing SPF of 7. So it will return 0 because there is no prime factor found. But what is the actual smallest prime factor of 7? It is the 7 itself, which is prime. So we can change a small code, and we can traverse all the numbers from total maximum limit. And if we found SPF j is equal to 0, which means that it is a prime, and we can replace that by that because it is the only divisor and it is smallest prime factor so far. So SPF of j is equal to j. And now coming to this question, we can take input, and initially the height of the tree is 0, and now till the number is not equal to 1 and SPF of num is equal to num. This means that the number is prime. So if we found a number, we cannot update the next because they have specified that it should not be 1 and the number itself. So we can replace only if we have a non-prime number. So we can loop till the number is equal to 1 or the number is prime. So we can divide it by the smallest prime factor because we want the largest number, and we can increment the height. Finally, we can print the